The first data structure we're going to be covering is the array. Now, I understand the array is a pretty common data structure that's taught in many programming classes, and that many of you might already know the properties and uses of an array. So on your screen now and in the description is going to be a timestamp which will take you past the general information on the array to the point in the video where we start talking about the array as a data structure, including its time complexity equations, storage methods, and more. If you're not as versed in the array or just want a general review, then stick around, because right now we'll be discussing what an array actually is, how we create arrays, and how we reference items within an array, as well as the idea of a two-dimensional array. Let's begin. So an array is fundamentally a list of similar values, which makes sense, because if you remember, we use data structures to store sets of similar information so that we can easily use that information. Basically, arrays can be used to store anything: usernames for an app, high scores for a video game, prices for an online shop, pretty much any list of values which are fundamentally similar, meaning of the same type. So integers, strings, floats, etc. Any primitive or advanced data type that you can think of can be stored within an array. Now, every item in the list of data is referred to as an element of that array, and we call this collective total of elements the array. An array will also have three attributes, the first being a name for the array, the second a type for the array, and the third a size for the array. Let's start with the name. The name, if you could not tell, is simply a name for the array, which can be used to reference it. Say, for example, we had an array called names, which contained a list of company employees. And then we also had an array called salaries, which contained a list of salaries for those employees. If we wanted to search through the list of names, we would do so by referencing the names array with its name. This way, the computer knows that you want to search through that specific array and not the salaries array instead. This works vice versa, of course, if we wanted to search through the salaries array instead. Now, another thing to note really quickly while we have these two arrays up is that these are also an example of parallel arrays. Parallel arrays are two or more arrays containing the same number of elements and have the property where each element is related to the element in the other array or arrays of the same position. So, from our example, we can say that the first element in the names array, John Smith, corresponds to the first element in the salaries array, the integer 10,000, meaning John Smith has a salary of 10,000. Parallel arrays are a good way to have multiple bits of information about one entity be stored in a way that is easily accessible. This is also really good because, as you'll see later, we actually can't store differing types of variables in the same array. So we couldn't have the salary integers be stored in the same place as the name strings. Alright, tangent over. Let's get back to the attributes of arrays. And the second one we'll be talking about, the array's type. Now, an array's type is simply what type of information is stored or will be stored within that array. One of the biggest stipulations about arrays is that it has to hold all the same type of information. So you cannot have an array containing integers and strings. It would have to be an array of only integers or only strings. This works for any type of information you would want to store within the array, meaning every element or spot within the array must be of the same type. The third and final attribute that an array has is a size. The size is a set integer that is fixed upon creation of the array. It also represents the total amount of elements that are able to be stored within the array. Additionally, an array's size cannot be changed. Now, I'll repeat that again because it's extremely important. An array's size cannot be changed once created. When you write that line of code which instantiates an array in your code, you give it a defined size or fill it with elements until it has a defined size, and then at that point it cannot be changed by conventional methods. This is actually pretty rare for a data structure, and it may seem really counterintuitive and useless, but later on when we talk about an array's efficiency, you'll see that this is for a very specific reason, and not just to be annoying to the programmer. So there you have it, the three attributes of an array: a name to reference it, a type to fill it with, and a size to control it. Let's now shift focus and talk about how we actually define an array ourselves, how we reference and change values within an array, and then dive into the idea of two-dimensional arrays. So there are actually two different ways to create an array in most languages. You can either populate the array with elements that you want contained within the array right then and there, or you can set a specific size for the array and then slowly populate it later on in your code. We'll be discussing how to do both, starting with the first method, creating the array with elements as soon as it's instantiated. Now, defining and filling an array as soon as you create it is mainly used for when you already know which values are going to be held within the array. For example, let's say you're creating an array which is going to hold the salary of 10 different workers in a building, and that information is being read from a text file. Well, you already know the salaries for those 10 workers from the text file, and so you're able to immediately populate the array when you create it, and then you'll have that information as the program runs. The way you do this varies amongst different programming languages, but it's shown here in 3 different languages, Java, Python, and C#, to give you a basic gist of how this is accomplished. All 3 of these lines of code will create an array of size 3, containing the numbers 1, 2, and 3. You can see that all of them involve the declaration of an array name, which is then set equal to the values you want to include within the array and encapsulated by some sort of brackets or braces. This isn't 100% how it's going to be for all languages. As you can see, Java and C# require you to define the array type, whereas Python does not. But for the most part, this is the syntax that it's going to follow. Again, that's name of array set equal to list of values separated by commas and then encapsulated by brackets. This also develops the size of the array for you automatically. So going back to our numbers array, since we populate it with the numbers 1, 2, and 3, the array would instinctively have a size of 3. If we were to say go back and add in a 4th number when we define the array, the size would dynamically increase to 4 the next time we run the code. Now, the second way in which we can instantiate an array is by setting an initial size for our array, but not filling it with any elements. This would be in the case that you don't actually know which type of information you're going to store in the array, but will as the program runs through. This is most common in the case where the end user will enter information into the program, and then that information will be stored inside the array. Shown on your screen now are 2 ways we can do this in Java and C#. Now notice there is no Python section, because of the fact that creating populate-later arrays in Python is not conventionally possible without the use of more advanced data structures or packages. You can see, however, with Java and C# that just as with the other example, there are slight differences in the syntax on how we do this, but generally it's going to follow the same set pattern. The type of the array, followed by a name for the array, which is then set equal to a size for the array. Remember, this size is final and cannot be changed outside of this initial call. If you create an array with size 10, but then later in the program find that you need more space for the array, you can always go back to where you define the array and change the size. But after the declaration of the array, there is no conventional way to increase the size of the array. You may also be wondering what the brackets mean, and that's just a way to signify to the computer that we are creating an array and not just a variable or some other data structure. Alright, now that we know the 2 different ways to instantiate an array, let's talk about how we as a programmer actually get information that is stored within the array. And the simplest way to answer that question is through the means of a numerical index. An index is simply an integer which corresponds to an element within the array. Now, the most important thing to know about indexes is that for a certain array, they begin at 0 instead of 1. So if we have an array of 10 elements, the first index would actually be index 0, the second would be index 1, and so on. Now, to retrieve information from an element within the array, you do so by referencing it using both the array's name and the index number of the element you wish to retrieve. Say we have our array called numbers here, which contains the integers 1 through 10. To print out the element at the 5th index, in this case the number 6, we would call the array's name, in this case numbers, and then in a set of brackets we would place the index we want to reference, so in this case the number 5. What this code is basically saying is print out the 5th index of the numbers array, which again is the integer 6. Now, because indexes start at 0 instead of 1, it's important to note that to get the 10th element in the array, you would actually need to reference it using the number 9 as its index, since there is no 10th index. If you do end up making this mistake, it will result in an out-of-bounds error, as there is no 10th index in the array. Referencing an array's index is also how we replace elements within the array. Continuing with our numbers array, let's say we wanted to change the last element in the array, the integer 10, to be the integer 11. what we would do is reference the 9th index of the numbers array, the one which contains the integer 10, and set it equal to 11. This tells the computer to take the element at index 9 and replace it with the integer 11, essentially swapping out 10 for 11. Now the last thing I want to talk about before we jump into time complexity equations for an array is the practice of putting arrays inside of arrays, because you can actually do that. An array with an array at each element is known as a two-dimensional array. Think of a two-dimensional array as a matrix. It's similar to any other array, except for the fact that instead of, say, an integer at each element of the array, we have another array with its own size and indexes. Two-dimensional arrays are useful for a variety of purposes, such as if you were programming, say, a chessboard, a bingo board, or even an image, where each element in the 2D array contains an RGB value, which, when combined, creates an image. Now, referencing an element within a two-dimensional array is mostly the same as with one-dimensional arrays, except you need to give it 2 indexes instead of 1. The first number would be the column you want to reference, and the second number would be the row you want to reference. By combining these two numbers, we can single out an element within the 2D array that will then be returned to us. As an example, let's create a two-dimensional array with 16 names contained within 4 rows and 4 columns. Now to access the name Carl, you'd first single out the column the name you're looking for is in. In this case, Carl is in the 3rd column, meaning it's in the 2nd index. Next, you would single out the row of the name you're looking for. In this case, the name Carl is in the 3rd row, so again we would use the 2nd index to reference it. So there we have it. The name Carl is in the index location 2, 2. Two-dimensional arrays are just the beginning. You can also have 3-dimensional arrays, 4-dimensional arrays, and so on for containing a large amount of advanced data. But 2 dimensions is where we're going to stop for today. Alright, that concludes the background information on arrays. Now that we know what they are, let's actually talk about arrays as a data structure. This is where we're finally going to be using our big O notation knowledge from the previous episode to judge the array as a data structure. We'll be going through the 4 criteria we talked about previously: accessing elements within an array, searching for an element within an array, inserting an element within the array, and deleting an element from the array, and scoring it on how efficiently it can complete these tasks using big O notation time complexity equations. Let's start with accessing. Now, accessing an element within an array can be conducted in instantaneous O of 1 time. This means that for any element within your array that you want to know the contents of, you can do so immediately. This is something very unique amongst data structures and has to do with the way that the array is stored in memory. For example's sake, let's look at a fake portion of memory in a computer. You can see we have some information near the beginning, maybe some integers or strings we've initialized. That's not important. What's important is that when we get to the part in our code which defines an array, we already know exactly how large the array is going to be, either because we've populated it with elements or given it a definitive size. This means we also know exactly how much space we need to reserve in the memory slot for that array. Combining these two pieces of knowledge also means that we can instantaneously figure out the location of every single element within the array by simply taking the starting location of the array in memory and then adding to it the index of the element we're trying to find. So let's say our array we reserve space for in memory now contains 3 elements, each of them integers, and we want to know what the element at the first index is. Well, we know that the array starts storing data here, and we also know that every element within the array is stored contiguously together in memory. So by taking the starting location for the array and adding 1 memory location to it, now we know that's where the first index of our array is going to be and can return that stored value appropriately. This is the main reason why array sizes cannot be changed, because all of the information must be stored in one place so that we're able to do this. The contiguous structure of an array prevents you from adding space to the array because it literally can't without breaking up the information and adding in the space to store new elements down the road, away from your initial array. This would make accessing elements instantaneously not possible. Hopefully, now you can see why accessing an element within an array is O of 1, as well as why array sizes are final, because not many other data structures allow you to have instantaneous accessing power, meaning arrays have a huge edge on the others in this functionality. Alright, let's move on. Now searching through an array is O of n, because, for the most part, you will be working with unsorted arrays, those being arrays which are not in alphabetical, numerical, or some sort of order, meaning that to find an element within the array, you have to search through each element before you can find it. This is known as linear search, and if you want to know more about it, click the card in the top right corner and it will take you to that section of our Introduction to Programming series. A link will also be provided in the description. Now, while there are faster ways to search through an array, those only work when the array is sorted. So for a basic array, searching through it to find a particular element is going to be O of n. Now sure, there are going to be cases where the element you're searching for is the first element in the array. But when working with big O notation, we always use the worst case scenario. And in this case, worst case scenario is that the item you're searching for is the last element in the array. This means you have to check every element before you can actually find the one you're looking for, which for an array of size n will take n operations. Finally, inserting and deleting elements from an array both have an O of n time complexity equation. For inserting, this is because inserting an element within the array requires you to shift every element that's after the index you want to insert the value at to the right one space. For example, if you have an array of size 5 with 4 numbers currently in it, and you would like to insert the number 1 into the array at index 0, you first need to shift every element to the right of index 0 to the right 1, essentially freeing up the space for the number 1, while also retaining all the information currently stored within the array, before you can actually insert it. This requires you to traverse through the whole list of size n, which is why the time complexity equation is O of n. Now sometimes you might not have to shift the whole list, say in the case you had the same array of numbers, only this time the 4th index was free, and you wanted to insert the number 5 into the open spot. Now since you don't have to move everything to the right one in order to make space for this new element, doesn't that make inserting into an array have a time complexity equation of O of 1 because you can do it all in one operation? Well no, because again, when we talk about a function's time complexity equation, we always refer to it in the worst case scenario. The most amount of operations that we're going to have to conduct before we can insert an element within the array is n, the size of the list, making its time complexity equation O of n. Deleting an element from an array follows mostly the same idea. You simply shift every element to the right of the one that you want to delete down one index, and you have essentially deleted that element. Again, let's say we had an array of numbers 1 through 5. Only this time we want to delete the number 1 at the 0th index. What we would do is set the 0th index to whatever is contained within the first index, making it 2. And then we repeat this process until we get to the end of the array, and then set the last element in the array to be some null value. This deletes the element from the array by basically replacing it with the value to the right, and then this process is repeated until it frees up a space at the end. In the worst case scenario, we're going to have to shift every element down one, making deleting from an array also have a time complexity of O of n. So there you have it, the 4 time complexity equations for an array. Accessing is O of 1, and searching, inserting, and deleting are all O of n. Now let's talk pros and cons. Arrays are a really good data structure for storing similar, contiguous data. Its ability to access any item in constant time makes it really good for programs in which you want to be able to have instant access to the information contained within your data structure. It's also a lot more basic than some of the other data structures we'll end up talking about, and so it's easy to learn and master. Some disadvantages of an array are the fact that the size of the array cannot be changed once initialized. Inserting and deleting from the array can take quite a while if you're performing the function on larger datasets, and if you have an array which is not full of elements, you're essentially wasting memory space until you fill that index location with a piece of data. Overall, the array is a pretty reliable data structure. It has some flaws as well as advantages. A program you write could use an array if need be, and it would work fine. But maybe sometimes you want a little extra functionality, and that's where the more advanced data structures come into play. Speaking of which, next up we're going to be covering something very similar to an array, but also very different: the array list.